Hello, Professor. Good day. This is question 8 from the packet. It's the straight eighth one, the eighth question. Evaluate the surface of the force of the vector field, ds, where the force of the vector field is y to the fourth plus cosine z, comma, z squared natural log of x, comma, y to the power of x plus y squared, plus 3z. And S is the surface of the figure shown below. So because we have two different ways of doing this problem based on the last chapter given to us, this is now, I would choose to execute this problem doing the final chapter's method, which is the divergence of f, which is div of the vector field f, integral by the surface of the trip over the triple integral based on the domain restrictions. So if we take a look at what we did, first off, this is just the problem statement up above. And step one, the first initial step is to, again, find the divergence of f, div f, which is div of the vector field. Now that is just del dotted with the vector field. If we take a look at our vector field, we notice that if we take the partial of respect to x with the first quadrant, there is no x on that quadrant. So we can go ahead and cancel that out, and that partial is 0. Then the following would be the same because there is no y component to that second interval. We can go ahead and take that out. The third one, however, does have a partial of z. The first one, e to the x plus y squared, can be taken out entirely, but we still have a 3 plus z. So the partial of 3 plus z will just be 3. Now that we've figured out our divergence of f, div f, we can go ahead and now, using that, try to find and figure out our bounds to go ahead and do a triple integral to find the solution. So this figure is a little bit simpler. However, it was not to me. So I'll explain it a little bit more in detail because this part, for me personally, is a little bit more difficult to see. So if we notice, we have a square in the bottom, which in my interpretation means that I can go ahead and hold those two as constants. So the x and the y can be held as constants. So it goes from 0 to 2. So that would be my domain for the x component. For the y component, it goes to 1. So it would be 0 to 1. The third component, which is the z component, has to be of two variables because it is restricted upon those two variables on where the domain or where the points of the function will be in that domain of z. Now, what does that mean? Basically, that means that if the function goes from y to x, and those are the variabilities of it, if we notice, we see a little bit of a slope from the start of z to the finishing of y. Now that would give us a line slope, which will give us the slope that will give us the domain of the z. Now, when it's 0, the domain of z is 1. And then all the way following up through that domain is down dependent of 1 minus y. Hopefully that explained it a little bit better. That's something I'm still personally working on. And now, since we have that, we can now go ahead and input that into our triple integral. So because z, the component of z is based on a function of y, I decided to go ahead and integrate these three in this specific way because z is dependent on y, and I believe that it would be a lot easier for me to use y next. And then x can go ahead and be a final since it's just constants. And although y is constants as well, I just think it would flow a lot better. So looking into this, the first thing I decided to do, the first thing I decided to do was integrate that first domain. Now the integral of dz to 3 is just z. And whenever you put the bounds between, 1 minus y and 0, you'll just get that 1 minus y. So I plugged that in. And now I ended up getting 3 times 1 minus y, dy dx. The second part, I went ahead and threw the constants inside and then split them both apart just to integrate them a little bit easier. I ended up getting 3y from the domain restriction of y from 1 to 0, and the same vice versa, except for 3 halves plus y squared over to the domain restriction of y to 0. Now, when you subtract the two of them, you end up getting just 3 halves again. So then after that, you have your final component, which is x. Now it is from 2 to 0. And when you integrate this function, you end up getting just your x. And when you plug in your x for the 2, so you get 3 halves times 2 minus 0, which will end up canceling out the 2, which will end up just giving you 3. Thank you. I appreciate you listening to this presentation. This is my first video on, again, question 8 of the first packet. There's the first test in the packet, I believe.